Okay, well, good morning, everybody, and welcome to the last of the Friday seminar series of this season. And so, it's just a minute after we'll get started here, but I'll start with the introductions of Dr. Droxler. We're really fortunate to have him come give this final talk. So, Dr. Droxler, until his recent retirement in July of 2020, was a professor. And he's currently a Emeritus professor at the Department of Earth and Environmental and Planetary Sciences at Rice University. His research is focused on studying the morphology and the sediments accumulating on slopes and basin floors surrounding the coral reefs and carbonate platforms. Over the past 40 years, he has conducted research programs in the Bahamas, offshore Jamaica, along the Belize margin, in the Western Gulf of Mexico, in the Maldives, along the Australian Great Barrier Reef, and in the Gulf of Mexico. Did I mention that already? Sorry. This is quite a long intro bio here, you guys. So let me see if I can get through it. And Papua New Guinea. The main focuses of Dr. Droxler's research as a marine geologist and oceanographer include the regional and global evolution of coral reefs, the oceanographic, climatic, and sea level records archived in the sediments deposited around reefs and carbonate platforms. Dr. Droxler has focused on his research on some ancient fossil reef systems, and particularly recently, some late Cambrian microbial buildups spectacularly outcropping in Central Texas. His work has been funded by the National Science Foundation, the American Chemical Society, and numerous grants from oil and gas companies. Dr. Droxler has published more than 150 scientific publications and has edited 2 books, including Earth's Climate and Orbital Eccentricity, the Marine Isotope Stage 11 Question in 2003. Before becoming an assistant professor at Rice in January 1987, he was a postdoc researcher at the University of South Carolina from 85 to 86, received his master's degree, equivalent from the University of Neuchâtel, thank you, in Switzerland in 1978, earned his PhD from the Rosenstiel School of Marine and Atmospheric Sciences at the University of Miami, Florida in 1984. Whew, sorry, that was hard. I'm not sure why. I had 2 cups of coffee this morning. So we're really pleased to have Dr. Droxler here. And of course, I got to meet him out in Mason County as I was doing my mapping of some of these Paleozoic sediments. He ran a field trip that I joined and it created a partnership from then on. And he helped us with some of the stratigraphy out in Mason County. And so he's a co-author on a state map program map here that the Bureau is putting out. And so we've got the only Friday seminar series speaker to bring rock. So we actually have core. So those of you who are remote. So we've got this up in the front. So with that, I'll let Andre get started. Okay. Thank you.
Wow. Thank you, Brian. Yeah, rocks. But I'm not going to talk about rocks today, but this is a collection of cores that we collected around Mason in a very specific place in a private ranch that was closed for 40 years, Mr. Shepherd Ranch, the Eagle Ridge Ranch, just south of the Llano River. And we were allowed not only to do research there, but also to drill. And we drilled something like 200 of these cores by hand, thanks to my students and myself as well, but most of my students kind of helped. And when I retired at Rice, I was told that this collection, had to go. So I'm very grateful that BAG accepted to host this course, and they are now, here at the BAG. And this is a very dear collection to us because we drill it by hand, and so we didn't want to get rid of it. And I'm hoping that I'm going to be able to, through the BAG, have a chance, to publicize this core collection, and hopefully other scientists will be able to use this.
Show what we're talking about. Some of our folks here who are not in the room, I don't know if they can see this, Chuck.
Yeah, maybe after the talk, you can come, and it's here. So, and I'm thinking of, and I spoke with Linda to create maybe a one-day workshop where I would work all about kind of this our story. We published several papers already on this microbial reef Upper Cambrian, and use this workshop to showcase this core collection, and always open to do field trips. Okay, well, today it's a very different world. As Brian mentioned, I am really a marine geologist and oceanographer. So I did all my life, I did work going at sea on big ships. It was my dream coming out of Switzerland, which is very odd when you are from Switzerland, but sometimes it's when you don't have something that you want to get it. So, and I did some work, as you mentioned, in many places, but one location I did work for many years now is the Maldives. And so today I'm going to talk a lot about the Maldives, but we published a paper with my co-author, Stéphane Jory. He is a former postdoc. He is now a marine geologist and oceanographer at Ifremer in Brest, in Brittany. And I'm there as an invited professor now. Every year I go for 2 or 3 years. So we published this paper on the origin of modern atolls. And this, you would say, this title would not have been, would not trigger too much interest, maybe. But if you add to the title, challenging Darwin's deeply ingrained theory, this became quite a topic of interest, first in the media, but also in the academic world. So I'm going to try not to showcase today the reason why we think we should abandon the model, the Darwin model, published, as you probably know, in 1842, even well before his evolution, masterpiece in 1860. And I will explain to you why, we still teach this. It's everywhere on the web. It's in every museum, and it's such a beautiful model. So easy to teach to students that we still do it and again and again. But there's a good reason to kind of move, to another model. The model I'm going to show you is not a model of our own, but we have added on data set to really prove that, kind of the Darwin model need not to be put aside. So what's an atoll? So first, the word atoll is a word from the language spoken in the Maldives, atollu. And an atoll, so there can be kind of different shapes. The first one here on the left is Goidu Atoll. This is in the Maldives, but it shows very well, the definition. It's a ring-shaped island or reef that surround a lagoon. Yes, that's kind of the definition of an atoll. The one on the right is North Malay Atoll. It's much larger. As you can see, it's 48 kilometers in length. And there's, a few islands that have been established themselves on top of this coral system. Very few and very small one. One of the larger one is this Malay Atoll, kind of there. The Malay, on the Malay Atoll here, there's one island here, and it's Malay, it's the capital. And I just want to show you, kind of the situation there. It's about 2.5 square miles, 200,000 people live there. And the elevation, maximum elevation is 2.3 meters. And just recently, 3 years ago, the Chinese built a bridge between here, the main airport, where all the tourists come in. And again, there, kind of the airport is at sea level. For instance, during the major tsunami in the early 2000s, a plane was ready to go, a big jet, and suddenly the runway was totally covered with water. So the Maldives is a place, kind of in the front of climate change and sea level rise. So as I mentioned, kind of these atolls, can be large, small, different shapes. This is Ari Atoll. This, you can see, the scale, it's about in length, it's about 100 kilometers. And you have a smaller one, kind of there. This is Razdu Atoll. And so this one is about 10 kilometers. They have different shapes. And even if you look at larger atolls like Ari Atoll, you can see that the rim of this atoll is made of smaller atoll, like almost the Russian, kind of Russian dolls. And so this one here is about 2 or 3 kilometers in diameter. And this I name kind of pharaohs. So the smaller atoll, about a few kilometers in diameter would be called pharaohs. So you can see that already atolls can be, even within the Maldives, can be very much, kind of different scale and different shapes. So Darwin was obviously a British naturalist. It's, when you see a picture like this, you would not even know that this was Darwin, but this is Darwin young, 22 years old. And as I see myself, kind of at 22, and when I have a picture of myself now, you can see that it's quite different. But so what he did, in 1831, he ended up becoming kind of the geologist on this 5-year-long journey around the world on the Beagle. Already at that time, scientists had already kind of were questioned by the atoll themselves. What would be the atoll? I don't want to go into the details, but they already had this idea that yes, the atoll kind of had something to do with corals, and these corals would be limited in terms of depth. So they would be colonizing the top of often volcanoes, and these atoll often would be surrounded by extremely deep water. So they were very, they already had some ideas about atoll themselves. So this is the way kind of we would recognize Darwin. That was at the end of his life. And so what he did, and I don't know if any of you would know, but he published in 1842 this amazing publication, The Structure and Distribution of Coral Reefs. So imagine him on the Beagle, very small vessel, for 5 years. He did spend a lot of time on land because it was the expedition was really kind of to map coastal areas. For instance, he spent a lot of time in Tierra del Fuego. He spent some time in Chile. Obviously, he went to the Galapagos, where he did some of his basic work on evolution. And but what he did, which is really incredible. Oh, and before kind of this, I just want to ask you a question. Yes, what is a reef? So when I ask a question to students or even colleagues, very quickly, kind of we come in with biogenic reefs. Yes, but a reef is not really, by definition, just a biogenic reef, meaning so what it's really a nautical chart term, and it's a positive relief, shallow enough and hard enough to sink your boat. So as a matter of fact, if you remember when the Exxon Valdez, kind of hit a reef, it hit Blight Reef, and you think Blight Reef in Alaska? Well, it was a piece of hard rock that was too shallow, well marked, by the way, and obviously too hard, kind of for the Exxon Valdez to go through it. So this is kind of the idea of reefs, and when you think about it, kind of coral reefs are a major hazard, and because of this, the Royal Navy, which was a superpower in the kind of 1800, in particular in the early 1800s, what they did fabulous mapping of these hazards. So they didn't do the mapping of reefs for the pleasure of knowing where the reefs are for academic reason, but mostly because they wanted to avoid them. And so, for instance, this is a figure of that 1842 publication by Darwin, and it is kind of the archipelago of the Maldives, this series of very large atolls that spread about 800 kilometers. And it's pretty incredible when you compare this with a satellite image of this. Yes, it's almost, kind of, I mean, the proportion of the atolls are there, the spreading of the atolls, the fact that there's missing atolls, kind of in that part of this western chain of atolls. So to me, it's already a mystery how they were able to map this in such accuracy. It's even more so when you would go to this atoll here called Malos Maludu. And so if you look at this, the details of this, and now you bring kind of the satellite image, you realize that there are some powerful methods to map these reefs that are not even exposed. Most of these reefs are very shallow water, but they were able to really map them very, very well. And this only because they were hazards, yes, not for academic reason. So what Darwin did, probably he was bored to death, on the Beagle. They had all the charts available when they left, kind of on for their voyage. So he made a major compilation, and this is absolutely amazing when you think about that. With all of this data he had, and he had books as well, he created, this map. And this is part of his 1842 publication. So he kind of, on a map, he compiled all the reefs, the coral reefs that he was able to put his hands on. If now you put kind of this or part of this map with a modern map today, you can see that no, it's almost 1-to-1. There's one, if you go kind of back here, interesting enough, and I've done a lot of work in Belize, and at that time, I guess they didn't know that a reef existed in Belize. So there are a few, kind of a few exceptional places where you didn't know yet that this reef existed. But this is really a masterpiece when you think about it. This is 1842, but it also tells you about much the Royal Navy had mapped, kind of this reef. As a matter of fact, himself, Darwin didn't stop in any atolls beside one, Cocos, which is, here in the southeast part of India. And he did quite some work there. He went and dug some trenches. He has published. He published a few papers on, for instance, the action of parrotfish, how parrotfish produce sediments by chewing on corals. So he was really quite advanced. And so not only kind of Darwin created this map, but he now separated the types of reef that exist. And this is kind of from Darwin. So he defined fringing reefs, the reefs that are attached to land, barrier reef, the reefs that are somehow detached from the land and are separated from land with a lagoon, and atoll, the one that are not attached to any land, and this ring reef enclosing a lagoon. So with this, he came up with this amazing and beautiful model how this happened. How do we go from fringing to barrier and to atoll? And at the time, people had this idea that vertical tectonic was the main way of explaining continents and the ocean. Obviously, at the time, they didn't know how deep the oceans were. They knew they were very deep, but they didn't know how deep they were. But they knew that, yes, the continent had been exposed. And even himself in Chile, he witnessed a major earthquake and could observe along fault line that some part of the land had been uplifted. So with this idea, he felt, okay, and this is not only himself, but most of the geologists at that time would say, okay, if the continents are being uplifted, the oceans have to be, subsiding. And so with this idea of the three types of reef and subsidence, he came up with this model. So these are figures, these are figures that he put together. So, kind of the first one, so it's a volcanic island surrounded by a fringing reef. He made, kind of this, I'm trying to see if I can, oh, here it is. He made, kind of this cross-section. All of this are not colored in his publication, but this is, his own figure. So you can see, the volcanic edifice with here in black, the fringing reef. And after this, he realized, oh yes, there are some islands, with a reef, and these are charts that are published in 1842, by Darwin. So these are all, all existing nautical chart. And so here, when kind of now the edifice subsides, now the fringing reef becomes barrier and enclosed, a lagoon between the edifice and the barrier itself. And the next one is an atoll, where you have a beautiful ring reef enclosing a lagoon. And now the edifice has subsided so much that it is completely covered by the carbonate. Marvelous. What he had, is intuition to be able to, first of all, to compile these reefs on this map, but also after this, to come into a dynamic model, how to explain, kind of how these reefs have formed. So this is the model that probably you are taught and probably you are teaching still today. On every oceanographic book, is what you find on introductory of a science book, in museum. It's the model is so simple and so logical that you would think it is the way, atoll are formed. There's one thing that, and you cannot blame him for not knowing, he didn't know at the time that we had major change in climate. And Agassi was the first one, at least in the publication, to demonstrate that, yes, climate has changed dramatically on Earth. We had large glaciation, and in consequence, so major change in sea level. So he had no idea that sea level would go up and down. As a matter of fact, sea level is going up and down in the late Quaternary at rates, 3 times of order of magnitude faster than any rate of subsidence of a volcano. So this is really overwhelming, for him. So with this, already in our 30s, we were aware of this major sea level amplitude change. For instance, kind of Hofmeister, Kühnen, and McNeil. And they came up now with this new model, this antecedent karst theory. The idea being that once you have a carbonate platform, even if you start now with an atoll, if sea level is not changing much, the production on this reef will be such that you would infill the lagoon and create a flat top bank. When sea level drops, now this shallow carbonate system is exposed to rain, and now you create a karst, kind of topography. And they even made a small model now here by dripping in the early 1900s, by dripping some acidic solution, and realize that, oh wow, this you create now maximum dissolution in the center of these blocks, and now you have minimum dissolution on the margin. So you create a karst system with a low in the middle and a high on a side. And now when sea level goes back up, it mimics this karstified morphology, and that's where the atoll can be explained with. So what we have done, we have not done anything else than just using this model, but trying not to come up with data that exists, data about sea level in the last 5 million years, but also data about different atolls based on seismic and morphology, and explain that yes, reefs are kind of fairly recent, and they are formed on top of flat top banks. All right. So also most of the idea was kind of the substratum of atolls had to be a volcanic edifice. There are very many examples where it's not the case. We do know a lot about kind of sea level. So with this, kind of I will try to show you, and using example from the Maldives, the Pacific, the Indian Ocean, and convince you that we need kind of to go ahead and use this karst methods or karst interpretation in order to try not to explain the shape of the atolls. So this is, as said, we know quite a lot about sea level change. This is not the latest one, I realize, but it's from Miller, 2005. This is 5 million years. This is today. And so this is sea level. This line here is today's sea level. So you can see that in a Pliocene, sea level was not changing much. The amplitude was in the order of maybe 20 or 40 meters. This is the beginning of the Northern Hemisphere glaciation about 2.7 million years ago. And since this, the ice volume on Earth, the Antarctic existed already, but the Antarctic, ice volume kind of increased as well. But mostly this here is the increase of ice volume in the Northern Hemisphere. And so you can see that we have maximum ice volume during this glacial time, and that translates into this very low sea level. And it's only when you arrive here, but 600,000 years that you have one of the first low sea level of about 120 to 130 meters below modern sea level. And you can see that sometimes, yes, even here, during this slow fall of sea level for 2 million years, you had time when we had what we would call this super interglacial, where sea level would have been at today's sea level or even higher. And the next one here is this major, and this is kind of a blow up of this, kind of last 800,000 years. This is the kind of the Bruins. the early burns show that sea level was never higher than today. And so, and here you have the largest amplitude in sea level change from about 120, 130 below modern sea level. And this was about probably 10 meters higher than today. So this is the first time that you have this major, kind of rise of sea level after this very long-term, drop of sea level there. If you look, at the at one time, here during the it's called the mid-Pliocene warm period, or the MPWP. It's about kind of 3.3 to 3.2 million years ago. We had an 800,000 year long warm interval, and this is, the delta rating that gives you a sense of the benthic and planktic delta rating, and give you how stable, kind of the climate was, and therefore sea level. So 80,000 years, sea level will have remained constant. On the other hand, if you would look at this marine isotope stage 11, this first major transgression in the from the midburns, this is marine isotope stage 11, is also the planktic and benthic. You can see that, and here it was a fairly warm one, but the sea level remained more or less constant for about, kind of about 30,000, 35,000 years. On the other hand, if you look at 5E, which is the previous interglacial, in 5E, sea level remained slightly higher than today, but only for half of a precession cycle, so about 12 to 15,000 years. So why is that so important? It's important because if sea level remained constant for such a long time, any atolls that would have existed at that time would become flat toe bank, meaning that there'll be enough production on this rim reef to infill the lagoon. And it's really what we see, that in this late Pliocene or middle Pliocene, we have flat toe banks. And it's on top of these flat toe banks that you can see, modern atolls that grew, on them. All right. So I talk about all of this. And so we use different examples. Mostly, kind of, we are going to spend time in the Maldives. We're going to spend time, in Mururoa and in Funafuti, and also in Basada, India. Okay. And interesting enough, most of these studies that, or the data we have in these atolls, I could ask you, why do we know so much about some of these atolls? Maybe I can ask the question. Nuclear explosion. So the nuclear testing, kind of was a fantastic, yield of data for us geologists. And the French, kind of in Mururoa, in Bikini, and Oatak, I mean, these atolls were drilled and drilled afterwards. Could you try to understand, the effect of this nuclear test? So there's always a good side, of some of our experiments. All right, so there's different subsidence. We have a lot of data from the Maldives, and we have also some data, from Basada, India. This is the work that Stefan Jory has been doing in the past, kind of 15 years. Okay, so here to reiterate now how big the Maldives are and how little exposure we have there. So there's about 1,200 pharaohs on these very small atolls, put together as 22 larger atolls. This is about, kind of 800 kilometers. So it goes from about 8 degrees of latitude to slightly below the equator. And so if now you try to now compare this with a real bathymetry data there, here you can see that it's not only extensive, kind of in latitude, but it's also, and we will see, it's also very thick. It's a very thick carbonate platform. And we know this because we have seismic, and I'm going to show you some of it, but also because we have drilled, we have drill site where we have penetrated the full carbonate system. So the Maldives, even though they looked very tiny, as a matter of fact, if you go on Google Map and you try to find the Maldives, you really have to go and zoom, and finally you find something. And so it's not, kind of a few atolls kind of coming out of nowhere. It's just the last phase of this very long-term evolution of this shallow carbonate system, which is kind of very large. Okay, so if we go now kind of and focus on this central part of the Maldives system, just to show you that we have a lot of data there. So we went there on leg 115. We had a new expedition, 325 in 2015. A lot of data we had done, with all exploration, surprisingly enough. Alpha Key 10 went there in the 70s. Shell went back there in it was in it was kind of in late 80s, and each of them drilled one well. Probably it was their contract. So for instance, kind of Alpha Key 10 drilled NMA1 here in the middle of the atoll, and it's a dream for geologists, yes, who can go and drill for 2.2 kilometers to find the volcanic plateau. And RE1 well, here is the Shell well. Here, drill, and I didn't mention, but no, this double chain of atoll are separated by this inner sea, which is about 400 to 600 meters of water depth. And the depth on either side is bathyal, yes, it's 2,500 to 3,000 meters of water. So here they drilled, and we will see, they drilled 3.3 kilometers before they reach the volcanic basement. So we have a lot of data here. And if now I'll show you the, a schematic diagram based on seismic on this line now here from the northwest to the southeast, this is what you would have. So here we have, kind of southeast, northwest. Here we have the existing North Mali Atoll. This would be Goidu Atoll there. And we have this inner sea. And this is the projected RE1 well. This is NMA well. And here we also, as academician, on leg 115, the Bob Duncan, who was the co-chief scientist, wanted to go and drill the basement, but with a journalist resolution, you could never go and drill for kilometers. So because we have good ideas, we went and drilled just on the top slope, and there we drilled some Miocene, but mostly Eocene carbonate. And after this, we drilled the volcanic plateau, and we were able to date it, and it was, kind of 55 million years ago. And I think I do have, no, I don't have this data there. But so here, 55 million years ago, and we saw another beautiful transition from the plateau. We also were able to wait. The igneous petrologists were able to show that, oh yes, this plateau had to be exposed and had subsided. Here, the RE1 well, we didn't have we had a sample there of the volcanic basement, but it was too altered to date. And here on NMA, we had also some samples, and at the base, it was 57 billion years ago. So what happened? So this was a plateau, and it is related to the hotspot of the island of Reunion. This is part of the Deccan Trap, hotspot. And so the Deccan Trap's being kind of the KPG, whatever, Cretaceous Tertiary. So the Cretaceous, Paleogene boundary at 65. So this is part of this hotspot, trace. It was a plateau exposed. It was tectonized. There's some very large graben, very deep graben in this, and it's the reason why the oil companies thought that this would be a good source of hydrocarbon. And at some point, very early on in the Eocene, in green here, the shallow water carbonate got established and continued kind of all the way to the Oligocene. So all the blue here is shallow water carbonate. And at some point at the mid-Oligocene, at the boundary between Oligocene and Miocene, a major anoxic event, and this was shown by the results of this IODP expedition 3559, almost fully drowned. Only the margin of this much larger platform remained and continued to aggrade on either side. And after this, prograde. And you can see that it's at the very end that you can see this atoll, yes. So the atoll that you can see have nothing to do with the volcanic basement there. Just the fact that the volcanic basement is very old, slowly subsided, but the form of the Maldives atoll is really part of another story. Just to show you here, a seismic line from a modern atoll to, kind of here, as I mentioned already, there are something missing. If you look at the western line of atoll, you can see these blue areas there. These are drowned platform, and they are about 250 meters in water depth, and they are very flat. And so if you go to kind of now on top of this one, so the north part of Ari Atoll is sitting on a much larger flat top bank. And so this line, you can see, kind of this is our flat top bank there, and with some seismic data, and this was one of my first PhD student who did the work on the Elf-Aquitaine data and could really show that, oh yes, so this was drowned, sometimes, kind of in a late Pliocene. And if you would go now kind of now here on the margin of South Mali Atoll, you have kind of the story here where we have the evolution of the system. So in the Neogene, we have this aggregating and prograding sequences up to about 3.1 million years ago. And after this, you can see kind of this, and most likely because of the sea level drop at the beginning of the Quaternary, by definition now. Now this system would be mostly exposed. You would have some deposition on the shoulder of this, and this would be about between 3.1, 2.5 and half a million year. And now you can see the next phase is this late Bruns, where you have now accretion, kind of aggradation, and this is when you create kind of this atoll today. So this was kind of the what we could see kind of the seismic. So you can now put this into perspective where kind of this Neogene and Pliocene aggradation and progradation would be at this time of the Pliocene when sea level was very much constant. This here would be during the time when we have this major drop of sea level there. It might be reflooded during this super interglacial here during the early Quaternary, and this late phase of aggradation and atoll phase is really only during the last about 400,000 years, since marine isotopes stage 11. Okay, we have, if we look, at an area, for instance, like I'm always kind of trying not to. Okay, here. So we are here, kind of now in Mali. We had a chance to go, and there we had, this is Mali Island, the black hole there. This is the island of the airport. So we did this beautiful multi-beam data set around the island. I don't want to go into the details, but because there's some major failure around the island, one of the jetty disappeared one night, and we were very concerned about kind of the capital, because as you can see, it's overbuilt and it's built on the edge. So we did this very nice with Dave Nahr from USF. We did this beautiful data set. So we can see already that yes, we have terraces. This is just on the slope, on the upper slope. So we have beautiful terraces. Now this is at minus 125 meters, last glacial maximum, and you can see this series of terraces. But also in sea there, we have on the seafloor, and because there it's not covered with Holocene sediments, because there's so much current, you can see this depression, and this is karst features explaining well, or at least kind of giving us some good line of evidence that yes, this system was exposed and karst existed. As a matter of fact, kind of this first atoll I showed in the first slides, this Atafu Atoll, which is owned by New Zealand, but it is well within the tropical areas. You can see even there that the lagoon itself with no sediments has this beautiful karst system, within the lagoon. And if we go now to Goidu, this was, kind of data set that we got from Boskalis, is a dredging company from the Netherlands, in the Maldives. The government, is trying not to gain some time. So what they do now, they try to find sand around this atoll and dredged and build up, kind of some of the islands. As I mentioned to you, kind of naturally, they are only 2.5 meters in elevation. So they try not to raise them to about 6 meters. In doing so, they usually kind of destroyed whatever is around the island, which is a bit kind of counterintuitive, for trying to bring this island to higher level to bring tourists, but you kind of somehow destroy the environment around the island in doing so. But so this was data to show you that we had seismic data from this lagoon. And so you can see, kind of this 2 lines there. you can see that, yes, we have partial infill of this lagoon, but you can see here the Pleistocene karstic surface, and the depth, kind of is about the same, 40 to 60 meters of this lagoon depth as the one that we have in Mali. And another, a quick example, here, this is Wasdu Atoll. And so this is the work by Everard Geschler. And here it can show kind of this Pleistocene surface, a little bit of sediments in the middle of the lagoon. And it drilled, kind of the one of these reef in Wasdu and reached the Pleistocene surface and dated the material. And it's dated at 136,000 years, about kind of the previous interglacial Emeritus 5E. And this will be the growth of the reef during the last sea level rise. As a matter of fact, kind of this rate of accumulation here, 7.25 kind of to 15 meters per 1,000 years, is much faster than kind of the rate of sedimentation in the lagoon. Here you can see also the infilling of the lagoon is not just by settling, but it's also by prograding from the high energy kind of reef. You can see there's a lot of material being prograding and infilling the lagoon. If you look kind of here on one of these furrows, you can see beautifully here the high energy system. This is a very small place, but you can see beautifully how this lagoon is being infilled with the sediments. But as I mentioned, you need a certain time in order to infill this atoll and create flatter banks that we did, that was done in the Pliocene. Okay, so this is just another example, kind of now to show kind of these block diagrams where we have kind of a segmentation of our platform on the either side of the Maldives, and after this we have these flatter banks at about 250 meters, and after we have kind of here the formation of Ari Atoll and Wasdu and Goidu and Malus Maduro there. Okay, let's go now kind of to Mururoa. Mururoa is a very interesting place, as I mentioned. It's because it was the location of nuclear tests, so they have a lot of data there. So not only they have wells within the lagoon, but they have also well along the rim. Some of these wells are even not vertical but oblique, so you really kind of understand well the system. And if you look, first of all, you can know what's the depth of the volcanic edifice below. So this would be kind of the top of the edifice would be about kind of 200 meters below the lagoon. But what you can see this shallow water carbonate. This is late Miocene and early Pliocene. And now with all this data there on the lagoon, but also kind of within the rim, you can see these flatter banks at about 3.1 million years. And after this, kind of if you see kind of this rim here is very young. It's in particular kind of mid-Bronze in age. And it is a stack of accumulation of reefs. And after this, exposure and reef and exposures. Yes. Okay. So some people know I've done some modeling on this, using sea level, and you come up, with this this is the data, and this is what kind of they came up with in terms of the modeling. So this kind of fits very well. Another atoll, Funafuti Atoll, it's a very interesting one. It's where kind of in the 1896 and 1898, they drilled a well to try to prove the Darwin model, that yes, you have a volcanic basement below. Unfortunately, kind of they selected an atoll where the subsidence rate was fast, so they could never reach, kind of the volcanic plateau or the volcanic edifice. And so, but recently it was revisited and dated, and again you can see that. So this is kind of the 100 meters in terms of the thickness, and you can see that yes, there are periods of time when you have aggradation, you have mostly unconformities and aggradation here, and all of this is mid-Bronze in age. And you can go even further down, and the dating is becoming more and more complex because there's some dolomitization. But again, this time of growth points out about 2 million years. There's growth, here at about 1.5 million years, and growth again at about 1 million. And it's interesting is within, kind of this super interglacial, doing this major drop of sea level. So in a place where we'd have high subsidence rate, you can see that, yes, this atoll existed prior, doing this major drop of sea level, because the subsidence rate would give, enough accommodation for these corals not to grow. So Basade, India, this is the work of Stefan Jory. And so this is a beautiful atoll there. Again, here, the series of terraces. So there's these terraces here, and by dredging, they know this is late Miocene in age. Another dredge platform here at 250 meters, this very flat platform. This is most likely this late Pliocene flat top bank. And after this, kind of now the growth of the atoll itself on top of this late Pliocene flat top bank. Okay, so just recently, I think in 2022, last year, a paper came out where they've done some work on an atoll, Meiji Atoll. And so they had also a very deep well there. And they were able to do modeling on how kind of this atoll could be formed. For instance, kind of they created through their model, kind of this 3D feature model of the atoll itself. They could see, kind of here, this is the rim. They could also see, some patch reef here, that some of these patch reef are as shallow as the rim itself. And with this, they were questioning, using modeling, and I cannot go into the details because we are getting close to the end. They were able to kind of do some modeling and try to say, okay, if we have a flat top bank to start with, and we have no karst, can we create an atoll? And no, with no differential dissolution, no central lagoon or depression, would occur, kind of there. On the other hand, and this is kind of since kind of the last glacial, the major glaciation in the beginning of the Quaternary. If now you create a surface, through dissolution, you can now create at the very end, you can create kind of this atoll features in this modeling. And so with the dates kind of there, you see, wow. So this atoll there are again mid-Bronze in age when they are formed. Before this, you really don't form major rim and deep lagoon between. And when you do this, and they were able to show that they have, kind of this growth, and I should go back, for 1 second, kind of here. So if these are fairly well dated in their well, and so they had this growth again at this super interglacial, like kind of we had mentioned in our paper, and also with the exception of this mid-Bronze interglacial time, only the MIS9 is missing, but all of the other one, are there. And so they would, kind of be, kind of related to this super interglacial there, but mostly, kind of the atoll themselves would be formed, during the mid-Bronze, since this major and unique first transgression from -120, to about plus 10. So this here is really formed, kind of the atoll itself, the morphology is really formed because of this 405 major transgression and sea level rise and sea level fall of very high amplitude, and never giving a chance to this atoll to be infilled because the interglacial is only 20% of this 100,000-year cycle. Okay, so here this is the conclusion of this model paper. So, well, as I say, kind of the numerical which suggests the atoll is most likely due to differential dissolution across the margin and the interior. The preferential reef accretion along the margin is mainly predicated, by the karst-induced morphology, and even kind of they were able to model kind of the patch reef within the lagoon. If this patch reef, this patch reef would be sitting on top of this karst, kind of towers of karst morphology, and so they will be able to accrete it. And so, and the beauty, kind of they came, that was kind of a nice paper, to really help us, because people would say, can you model this? So they did this, in Meiji Atoll, and so, came up, with a strengthening of this paper that we published. So in conclusion, the modern atolls, are most likely, based on this antecedent karst theory, well established, kind of sea level during the last 5 million years. Similarities are observed kind of in the atoll. If you go anywhere, I didn't mention, but in Belize, for instance, now we can really show that, for instance, Glover's Atoll is sitting on a flat top banks that is most likely, Pliocene in age. And so, kind of, this is our little model that we did, kind of in our paper. So yes, we started with the flat top banks during this late Pliocene. We have a rim possibly, formed in at the very end of the Pliocene. But after this, we have mostly, kind of, so the atoll are really starting on the flat top banks. And through major drop of sea level, we create kind of this type of system here, especially if we have high subsidence. If we have no subsidence, we have a major unconformity between, like in Merriwa, between 2.5 million years and the mid-Burns, there's no deposit because there the subsidence rate is very slow. And so during this major time, it's a major time for dissolution, and it's really here, kind of this atoll, are formed, kind of doing this mid-Burns when you have this unbelievable, kind of, and it's kind of almost the first time we see this, at least in the Cenozoic, this amazing 100,000 year cycle with a sea level amplitude of 120 meters, and this time when, the interglacial, are only when the atoll are formed are very short. They are only, 10 or 15,000 years in duration. Thank you very much.
Thank you, Andre. We have time for questions, please. Well, I'll get it started here. So there's a lot of reference to the basement, the volcanic basement that these are formed on, and the subsidence rate. So what's the spectrum of the roots of these? You mentioned the volcanic like hotspots, but are there big structural areas, for example, with fault movement that might affect the subsidence rate, or what's y'all's experience on looking at those?
I didn't want to add kind of this example in Belize. We have there the Belize margin is part of the Yucatan margin. It's where you had the Caribbean plate translating from the late Cretaceous to early Eocene. So you have this amazing tectonic ridges there because of this translation, some thrust. And so on this, and it's, if you look at Belize and you look at where the reefs are, and it's sometimes around the Oligocene, like Turneth, like Glover's, where they drill this, that the Oligocene reefs were established on this high tectonic ridges. And there on Glover's, based on data, and thanks to Xavier, who had access to this multi-beam data, but also some seismic that we have, that the modern Glover's itself is really the last phase of this very large flat top bank that existed kind of in the Pliocene. So yeah, so you don't need a volcanic basement to create an atoll. You need something that, some kind of a high that was subsiding slowly, and also you need this major change in sea level first kind of to create a karst morphology, and after this yo-yo of the last 400 500,000 years, where you have this 120 130 meters of sea level amplitude change.
So you plot out like rainfall and subsidence rate as well, because lots of Bahamian platforms don't have a karst system, whereas Glover's does look very atoll.
Yeah, it is an atoll, yes.
Karst and the Bahamian,
yeah,
but they don't have an atoll geometry and subsidence rates.
Yeah. It's interesting to see the Bahamas. When you think of the Bahamas as a platform, it's it's used as an analog for many of our old carbonate system. It's kind of a unique case in the modern world. The Bahamas has this large bank, flat top banks. The subsidence had to be very slow in the Bahamas when you compare with other kind of system. And so there are other flat top banks like Mascarene Plateau, in the Indian Ocean, but it's kind of usually covered by about 40 meters of water depth. But so, I don't think you could create, in the Bahamas yet anything is an atoll, because it was reflooded 7,000 years ago about, at least for the shallow part of it. And it was so high and never created kind of this karstic morphology of the other system. You would need, I guess, to expose the Bahamas for a while and now bring sea level much higher than what it has gone, kind of in a Holocene for the possibility of creating an atoll.
Right, I mean, it was exposed just the same as all the other systems, right? I mean, it's
Yeah,
not
yes.
like it wasn't,
Yeah.
and there's plenty of karst.
Yeah.
But
Yeah. So is it because of rainfall during the glacial, kind of glacial at this latitude were most likely, drier, kind of than at least the transgression. So the karst was never, kind of able to create, this depression in the middle. Plus, the Bahamas are just so large, yes. Such a large platform when you compare, with this platform that we have, kind of for instance, at these flat top banks in the Maldives, we are talking about, kind of maximum, 100 kilometers, but in width about 30 kilometers. Yeah.
yeah, but similar. I mean, they got Great Agua or Maiguana or all the other relatively small platforms. They don't do it. But the one thing we're noticing, which is a similar style, is that the aeolianites are not preserved in anything except for the kind of post 400 kiloyear stuff. So, when you go across the mid-Pleistocene transition and you start getting the real, because none of the other stuff, we have a lot of cores now and no aeolianites in the older ones. And I don't think they're a big part of any of these systems either, right? These specific systems.
I don't think so. I know there are, and some new papers came out of the northwest shelf of Australia, where you have this very long ridges parallel to the coast. I mean, flooded now, drowned. And when they drilled them, people thought that they were mostly, coral reef. But what they find out is mostly aeolianite. On top of which, some reefs, kind of got established.
Right.
So, yeah. So, it's a good point, to think, why do we don't have, atoll in a Bahama, kind of Great Bahama system? That's interesting. But the subsidence, I think, has something to do with it.
Yes, subsidence rate, rainfall rates.
Yes.
Ed Purdy was always a huge fan of.
Oh, he published some wonderful papers, yes, on trying to explain the depth of the lagoon, with rainfall.
Right.
Yeah. So that.
I always thought he was crazy.
Yeah, but I mean, it's interesting to realize that, yes, I mean, you need a substratum to create an atoll. And at least the modeling, kind of seems to say that if you don't have an original depression in the middle with a raised rim, a karstified morphology, you cannot really create, the atoll. At some point they were tried, kind of to think that, as we know, that the rate of accumulation, the rate of growth on this platform of the reefs is much faster on the margin, because that's where the conditions are better. So they tried in the modeling to use this, yes, to try not to show and I didn't mention it, but to try not kind of to use this preferential growth rate along the margin and say, can I make an atoll just by doing this on a flat top bank? And they cannot do it. So they really need to have this karstic morphology, as a substratum.
That slide you have up on the screen at the moment is just remarkable. And one of the things I didn't quite understand, maybe address, but I didn't catch, is why are these features so in the third dimension so beautifully symmetric or circular like this? What accounts for that aspect in the model that you suggested?
So you are saying that if you go back to some of this, I guess I would have to go back a long.
Just the slides that's on there now. There's some beautiful examples of these nearly perfectly circular features that our atolls apparently are vegetated in the middle here, but nonetheless.
So this, I would guess, would be, if you would drill them, this tiny little atoll, yes, or this island, which is most likely an old atoll that was infilled, during the Holocene, not the one with the vegetation, but you can see, the other one. If you would go, kind of, and this was a student of Gregor, did work in Glover's, and they drilled, but not very deep, but deep enough, kind of, to show that even though the patch reef within the lagoon of Glovers are sitting on karst tower. So I would think, even this regular spacing might be, drainage system that existed during the karstification. And all of this would be, kind of higher Pleistocene surface on top of which, kind of this atoll, we are formed. And it doesn't have to start just during this last transgression. It can really start, kind of doing this first big transgression between 12 and 11. And imagine, so now you have this karstification, this karst surface, you use this during this major early transgression, but now sea level goes down again. So whatever you had deposited during stage 11 would be partially dissolved again. You might even increase the dissolution inside of this former lagoon, because now you have even a higher relief, between the margin and the atoll. And you do this 4 or 5 times. As a matter of fact, if you drill, often probably have drilled some of these. I don't know if you have drilled below stage 5. So you have usually an accumulation of 4 or 5, kind of accumulation of reefal material separated by exposure horizon during the intermediate high stand, low stand. Same thing, kind of what Greg Gischler, kind of published in the rhomboid reefs, where they drilled. I mean, Ginsberg drilled this, but Eberhard published this. You can see also 4 or 5 of these stacked, kind of reefal deposit on the rim, and over this you see clays, doing the early bruns. So yes, so this is kind of, we have to think it's not only one sea level cycle, but it's 4 or 5 of these very high sea level amplitude change since the mid bruns that really changed the morphology.
What you're saying on Mark's question is that you've got karst towers and things are growing around the tower. So that keeps them.
Yeah.
And one of the things we were doing recently is comparing, and there are a lot of these Bahamian platforms, the morphology we think is driven by longshore drift patterns that are driving the cusps, so that they're actually growth features and not collapse features, has been previously suggested. And then you go to a place like the Maldives, and you just don't see that. There's no big longshore drift pattern there. Everything is very
well. It's monsoon related, yes. And so I didn't mention any of this, but the currents are very interesting there, because they are more or less kind of northwest to southeast or southeast to northwest. Sorry, I'm thinking more southwest to northeast and vice versa. So there are, kind of through the year, reversed. So this also kind of this monsoonal current might create also this symmetry, because it's not unilateral, current like we have, for instance, kind of, in the Bahamas or even in the Maldives. If you think about, the coast as this very longshore current, from north to south. And I mean, we kind of published this in 2013, the origin of barrier reef. We do feel, and now we have more data, that the barrier reef itself in Belize is sitting on an old silicic coastline. And the coastline was reworked, by longshore current that explain, kind of this curve of the reef. And and it's not doing this last transgression only, but it's mostly doing the midburns that you start reflooding this old coastline, and now you can add on 4 or 5 of these stacked reefal system, and you create the barrier. And the barrier, on the Yucatan margin, interesting enough, it's only when you have the Maya Mountains, kind of on the hinterland. If you go further north, there's no barrier. The reef is fringing. So in this case, I would argue that most of this barrier, this long barrier along the margins, are, reef that have colonized this low stand, coastal system during the transgression. And so that's kind of interesting as well. Yes, we can explain both the barrier and the atoll, with this major sea level change in the midburns.
What's the name of the reefs that are on the drainage pad, rhomboid shoals or whatever? That's the other thing. It's rather spectacular to look at it on the south end of the Belize lagoon. See those reef systems growing right on the old river channel, right? Well,
I mean, it was kind of, Ed Purdy, kind of thought, oh yes, this is tectonic. Ed Purdy thought that the entire margin in Belize is limestone. even though there's siliciclastic on the coast today, which is only siliciclastic if you go from Belize City down, he felt that the siliciclastic had really nothing to do with anything there. And so he would explain all this rhomboid, because they are rhomboid, it would be a two-stage of faulting system that would influence the karst and would create all these rhomboids. But if you look at the rhomboids, and we have compared this with some of the drainage system, for instance, or the fluvial system in Brazil, for instance, you can see kind of these braided channels where the levees are now colonized by forests there, and they look exactly like the rhomboid reefs, even scale-wise. Oh, see, Dong Choi, maybe that's what you are. Oh, Esker, Dominic Esker. Yeah. And but he didn't really prove it yet until, kind of Gregor, published this paper, this master thesis that was never published on this drilling of this rhomboid. And he really found out, this is clay. In the early burns, it's clay. So it has to be, these braided channel, levees that have been, kind of used, to create, these features. So these are small atolls in a way, yes, very small atolls, but.
Can I take a discussion to the deep Earth time? It's like,
yeah.
So it seems to me now, listening to you, I've been looking at a lot of Miocene, and then there's not many time in the Earth history when you have 100 meters sea level.
Yeah.
Maybe in the Miocene, and then maybe in the Paleozoic, the last big glacial. But you need this is now today is the Goldilocks window, right? Where we have organism that can grow fast, maybe the right amount of subsidence or whatever.
Yeah.
So one thing I'm curious is that I haven't seen much atolls in Miocene.
Even during the late middle Miocene?
I haven't seen much. Doesn't mean they exist.
Yeah.
They don't exist, but it's probably because the reef doesn't grow fast enough. Because there's plenty of karst. Maybe you can find a barrier or two.
Yeah.
There's no atoll there.
Yeah.
And then I was wondering, we probably shouldn't expect any atolls in sort of Permian time, like Carbonispheric Permian time. There's nothing that grows that fast.
That go to sea level like the reef, yes.
Yeah.
I mean, most of these reefs are fairly relatively deep, you think? Yeah.
Well, that northeast side of Tengiz, right? That weird.
Yeah.
They almost look like some of the modeling you were showing from one of those atoll modeling. experiments, I mean, I never really understood why, because the southwestern side doesn't do that, but that northeastern side of Tengiz really builds quite an impressive rim.
Yeah.
And Golden Lane is a classic, right? Cretaceous.
It grows super slow, so there's got to be.
Yeah.
You can't really say it's 100 meters.
Is it an atoll or?
It's a huge bucket.
Is it?
Yeah, it's
700 meters deep.
And it's Cretaceous, and the time the sea level would have been, amplitude change would not be that much, you would think.
And the Golden Lane would be a whole string of islands like this.
Yeah.
That went around. I mean.
Yeah.
Yeah, it definitely has that more.
And it has karst. That we can see on the seismic. There's
Yeah.
All around those.
Yeah.
For sure. Like huge karst.
Yeah.
100 meters.
Yeah. Maybe we don't know how much sea level changed in the Cretaceous.
Some periods, right?
I mean, there's some, there's some major, sequence boundaries, and sometimes you wonder how much the amplitude change was at that time. But yeah, I mean, it's an interesting way of looking, at atoll, and we are convincing people now, kind of to at least question, the Darwin model, and it's not to question him, but it's to question, kind of the way, he would use, to explain whatever he would use to explain it. And there are, for instance, kind of in Brest, there's some kind of a museum, oceanographic museum, and they are changing, the tropical hole there. It's called Oceanopolis, and they are changing, they are taking the model of Darwin out, and they kind of bring something like this, and there's even a movie. Now that this came to us, and it's kind of this, it's very interesting. It's this little star that falls into a lagoon of this Tahiti atoll, and the little star fall in love with the little star. And it's for kids, and it's for planetarium, and so the director of the movie came to us and he said, I just found out on the web that, you're questioning the Darwin model. So now the little star is telling, kind of the karstification, process to explain the atoll. So I think, and some people, even Jeff Netwara told me, oh yeah, it's a great model, but I'm going to continue to teach, the Darwin model because it's so simple. Why would you do this? At least explain that it cannot really work, the way it is. But anyway.
So there's one question online, and I think then we'll need to wrap it up. And that is that kind of touches on what you were just discussing. Do you completely discount the Darwin model of atoll development, or are there instances, perhaps examples where, yeah, maybe it could be a good model?
Yeah, I don't think we have some clear example where it could happen. It would mean that kind of the volcanic edifice would have been to be very recent. And with this yo-yo of sea level, you might have, kind of some potential kind of system similar to what Darwin and Blanchard, published a paper on Tahiti, where, you would say, you could explain something like this, but you would not explain kind of this idea that, yes, the barrier reef, the fringing becomes barrier. So it's kind of just vertical motion and becomes an atoll. And Tahiti is not an atoll yet. So you could always kind of say, yes, kind of the fringing could have become, the barrier. But I don't think, there's any example, where the Darwin model should explain this atoll. And it's too beautiful and it's too simple. But, with what he had, and I hope I was able to.
Cool. It's a pretty cool model, though.
Oh, it's.
The guys float around.
But imagine,
data,
I mean, and I hope, and I spent a lot of time at the beginning of the talk, to mention Darwin and what he did, the compilation of this map. And it's published in 1842, meaning that it's just data from the early 1800s. And to do a compilation like this, and after, to come up, oh, yeah, there are different types of reefs. So this fringing barrier and atoll. And from this, come up, with a model. It's pretty astonishing.
But it really matters. Complex, the fact that it's more complex.
Yeah.
Involved in much more dynamic Earth, where many processes matter and change over time matters. It's actually a really important thing for museums to have.
Yes.
The Earth is an integration of many processes that change dramatically over time. Is the message they should leave with.
That's
Not
right.
that things happen simply.
Yeah. Oh, exactly.
Understand that the intersection of many, as you were, I was just thinking how many different things you're talking about to create this morphology.
Yes,
And
yes.
That's an important museum worthy idea.
That's a good point.
Is the complexity of Earth processes, an active Earth process.
Yeah, imagine Darwin had this very simple way of looking at things because he had no data. I mean, they didn't know how deep the ocean was, below probably 200 meters, because they were using, kind of fathoms, with a line, kind of to measure depth. I mean, he did go and measure, the depth of some of the lagoon, for instance, in Karst. So they were, this very scientific, approach to it. But I mean, he didn't know that. I mean, glaciation. Even you talk to people around, and you start telling people that 20,000 years ago, sea level was 120 meters below. I mean, 80% of the population would think that you are crazy. And so, especially now in the context of sea level rise, and you tell them, my God, sea level was going up, meters per century, 14,000 years ago. I mean, it's just so dynamic. And I think it's a good point that, kind of Darwin had this very simple world to work with because he had such limited data. And with this, it still came up, with this interesting way of explaining things, like evolution, for instance. I mean, it's spectacular, yes.
Well, Dr.
So-
Droxler, thank you very much
Thank you
for a
very
wonderful
much.
talk.
Thank you. And thank you for the invitation.